All right, so have you ever stopped to think about what really makes our complex digital worlds tick? Or maybe more importantly, what makes it all come crashing down? Today, we're going on this kind of epic quest. We're going to dive deep into the logic that underpins all of our technology. It's a journey to figure out if we can actually build perfect systems, the kind that just never break.
So, here's our game plan. First up, we'll talk about this dream of a perfect system. Then, we'll get into the special language they invented for it, which is called temporal logic. After that, though, things get tricky. We're going to face down two huge challenges, something called the undecidable and another beast called complexity. But don't worry, we'll then look at the super clever ways researchers are tackling these problems and wrap it all up with what this means for all of us.
All right, let's kick things off. At the heart of this whole thing is a really simple, fundamental desire, right? We just want technology that we can actually, truly trust.
So, why do these complex systems fail? I mean, this is the core question, isn't it? We've all been there. Your app freezes, a website glitches out. Annoying, for sure. But what happens when that system isn't just an app? What if it's controlling the power grid, or a self-driving car, or a pacemaker? Suddenly, a failure isn't just an inconvenience anymore. It's potentially catastrophic. The stakes here are just incredibly high.
And here's the thing. To stop these kinds of failures, just testing for bugs, well, it's not going to cut it. You can't possibly test for every single scenario that could ever happen. It's just impossible. So what we really need is a way to mathematically prove that a system will do what it's supposed to do. We need a super precise language to lay down the law, to say, this system must always do X, or this system must never do Y for its entire lifetime. Okay, so how do you create these ironclad mathematical proofs? Well, a bunch of brilliant logicians and computer scientists came up with this incredibly powerful tool. You could honestly call it the hero of our story today. It's called temporal logic. So what is temporal logic? Well, it basically gives us a vocabulary to talk about time in a very specific, logical way. Think about pioneers like A.N. Pryor, who really laid the groundwork for all of this. With this language, we can finally write down rules like, hey, if a request is sent, a response will eventually come back, or this system will always stay in a safe mode. See, it's a language for making unbreakable guarantees.
But having a language of guarantees is one thing. It's kind of useless if you can't actually enforce those guarantees, right? And that's where this amazing technique called model checking comes into play. It is an automated technique, and you can totally think of it like a tireless, super logical detective. You give it the blueprint for your system, you give it your list of rules written in temporal logic, and it just goes to work, exhaustively checking for any possible way the system could break those rules.
Okay, everything sounds great so far, right? We have the language, we have the detective, but our quest for perfect systems is, well, it's not that simple. Because now we have to face our first great dragon, and this one comes from the very heart of logic and computer science itself. It's the concept of the undecidable. So what's the difference? It's actually pretty fundamental. A decidable problem is one where you can write a program that's guaranteed to give you a yes or no answer. It might take a while, but it will finish. But an undecidable problem? Whoa. For those, no algorithm can ever exist that can guarantee an answer for every case. It's like asking a magic 8-ball a question and it just spins forever. It's a hard, fundamental limit to what computers can do. And this isn't just some abstract, theoretical ghost we're chasing. It's a real problem. Researchers have found that as you try to make these temporal logics more and more powerful, to describe more complex things, you can actually trip over a line into the undecidable. It's a classic case of be careful what you wish for. This research from Breslin and his team, for example, talks about this dark side of logic. They added more expressive features, trying to make it better, but they accidentally pushed it over the edge, making their problems literally unsolvable by any computer, ever. Okay, phew. So let's say we're smart about it. We carefully design our logic to stay on the decidable side of the map and avoid that first dragon. But just as we catch our breath, a new one appears. And this one is just as scary. Let's call it the complexity beast. Here's the deal with this beast. Just because a problem is technically decidable, meaning you can get an answer, that doesn't mean it's practical. It might take until the heat death of the universe to get it. That's complexity. So look at this table, a logic like LTL. It's PS beast complete. Okay, that sounds scary, but think of it like a really, really hard Sudoku puzzle. It's tough, but you can do it. But then you look at something like CTL star. Its complexity is called 2 exp time complete. Now what does that mean?
It means that if you make the problem just a tiny bit bigger, the time it takes to solve it doesn't just double, it can square. We're not talking about a harder Sudoku anymore. We're talking about a puzzle that could literally take more time than the age of the universe to solve. So we're in a tough spot, right? We've got two dragons breathing down our necks, the undecidable and the impossibly complex. But in any good quest, this is the part where the heroes show up with some clever new tricks. Researchers didn't just throw their hands up and quit. Instead, they came up with some absolutely ingenious strategies to tame these beasts and actually make this whole verification thing practical.
And here are some of those amazing breakthroughs. For instance, some researchers figured out how to find decidable fragments. It's like they carved out these perfect little sweet spots from those big, scary, undecidable logics, keeping the good parts while staying solvable. Then you have guys like Vardy and Wolper, who came up with this automated theoretic approach, which is a fancy way of saying they cleverly transformed the logic problem into a different kind of problem that we're already awesome at solving. And then there are these revolutionary techniques like symbolic model checking, pioneered by people like Ken McMillan, which lets us check systems with a number of states so big it's just astronomical. We're talking more states than atoms in the universe.
Let's just zoom in on one of these for a second because it's so smart. It's called bounded model checking. The whole strategy is just super pragmatic. Instead of trying to prove something is true for, all of eternity, it says, hey, let's just check for a certain number of steps. Let's pick a boundary, a number k. We're essentially asking, does anything bad happen in the first, say, million steps of the program? This brilliant move turns a potentially infinite problem into a finite, totally solvable one. And it turns out this is an incredibly effective way to find a ton of real-world bugs.
Okay, so after this whole journey, staring down these impossible problems, seeing these super clever solutions, where does that leave us? What have we really learned? What's the big takeaway from all this? Well, it really all boils down to one fundamental trade-off. There's this constant tug-of-war between two things. Expressiveness on one side, that's what we want to say, all the rich, complicated rules we want to make. And on the other side, you have computability. That's what we can actually prove. Our ability to get a real yes or no answer. And the thing is, the more you pull on one rope, the more the other one gives. The more expressive you get, the harder it is to compute. This delicate balance, that's the real art of the possible in this field.
And that brings us to our final big thought for today. As our world gets more and more automated, and these systems run pretty much everything in our lives, this trade-off, it's not just academic anymore. It's absolutely critical. This whole quest for perfect systems forces us to face a really tough question. How do we choose between what we can actually prove is safe and what we just wish were true? I mean, where do you draw that line? The answer we come up with is going to define the safety and reliability of our entire technological future.